In order to obtain the general solving method, we need to introduce some new concept first. That is a state equation and an output equation. About state equation and output equation, you will learn in the course of signals and systems or in the principles of automatic control in more detail. We will only give you some of the simple introduction here. In such a second-order circuit, we might set UC and IL as the state variables. The word state here has appeared in many times in dynamic circuits. For instance, we have introduced the concept of the zero state previously. We said there, the zero state refers to the case of energy storage elements with no initial energy storage, or UC and IL being equal to zero. We have implied at that time that in fact the transition process in the time domain of dynamic circuits is determined by the change of UC and IL. Or more directly, it's determined by the change of the electric field energy on capacitors or the magnetic energy on inductors. So we choose UC and IL as the expression of the circuit state, which is appropriate. After set UC and IL as state variables, how to list the state equation? It's different from the second-order linear differential equation with constant coefficients we introduced before. The state equation is a first-order linear ordinary differential equation set with constant coefficient about the state variables. Specifically, we need to write that how duc over dt and dil over dt change with uc and il. And how they change with the external excitations. And how do we solve duc over dt? Here we naturally think of duc over dt equals 1 over c times ic. Similarly, dil over dt equals 1 over L times UL. It's a very important idea that we use to list the state equation. In other words, by using the linear combination of the capacitor voltage, the inductor current, and the external excitation, we can represent capacitor current and inductor voltage. For such a circuit, if we want to solve IC, we need to write KCL here. That is, IC equals IL minus IR. We conveniently use UC over R to represent IR, and then IC is expressed by the linear combination of the UC and IL. Similarly, if we want to express UL, we must use KVL in the loop. So that is UL equals US minus UC. In the two equations, IC and UL are expressed by the linear combination of UC, IL, and the external excitation. Next, substitute these two expressions into it. We can get that duc over dt and dil over dt are expressed by the linear combination of UC, IL, and US. We further arrange the equation into the form of matrix. That's like this. We call it the state equation. Then the so-called output equation refers to that in a circuit, we set a branch variable as the output, which is expressed by the linear combination of the state variables and external excitation. For example, in the problem, we can set IL as the output variable. It is very easy for this circuit because C and R are in parallel. So it's easy to write that IR equals UC over R, which completes the entire output equation. Similarly, we can also write it as a matrix form. It's like this. It is called the matrix form of output equation. For the state equation, we can write it as x dot equals ax plus bu in more standardized way, where the dot is the meaning of differentiation. A and B are matrix, U is external excitations. For the output equation, the more general form is y equals cx plus du. Similarly here, x, y, and u are vectors. C and D are matrix. We need to point that the state equation is a first-order linear ordinary differential equation set with constant coefficient, while the output equation is a linear algebraic equation set. With this basic knowledge, we can discuss that how to list the state equation and the output equation. There will be many discussions in the subsequent courses about it. Here, we only based on the circuit analysis. Here we recommend that you list the state equation and the output equation by using substitution theorem. In the general circuit as shown, there will be resistors and variable dependent sources in the box, but no energy storage elements. We put all the independent sources and energy storage elements on the outside. According to the previous introduction, we know that the state equation is to use a linear combination of the state variables and the dependent sources to express the differentiation of the state variables. So we naturally consider that the capacitor is replaced by a voltage source and the inductor is replaced by the current source, even though the voltage of the voltage source and the current of the current source are unknown. So the whole circuit becomes a resistive circuit. Though through solving the resistive circuit, we can get IC and UL, which are the current flowing through the voltage source and the voltage across the current source. We know that IC equals C times DUC over dt, and UL equals L times DIL over dt. So we will conveniently express DUC over dt and DIL over dt by the linear combination of UC, IL, and IS. Specifically, we look at such a RLC series circuit. Redraw the circuit with the previous approach. We can get such a equivalent circuit. What we need to do is to express IC and UL by UC and IL. It's clear that IC equals minus IL and UL equals UC minus IR. So we can further write IC equals C times DUC over dt and UL equals L times DIL over dt. So we can arrange it as a form of DUC over dt, DIL over dt equals 0 minus 1 over C, 1 over L minus R over L times UC IL. So we complete the listing of the whole state equation. As for the output equation, if we set UR as the output, for example, so for such a substituted resistive circuit, it's very convenient to write out that UR equals R times IL. It has realized the output equation.